In this video, we are going to make a design change to our platformer controller, which is going to bring it to the next level. We've already made a walk, a run, a jump, wall slide, wall jump, and a directional dash with all the controls you could possibly want: acceleration, deceleration, apex hang time, buffering, coyote time, air jumps, air dashes, etc., etc. And this is the exact player controller that I've been using in my game Surgebound, which is why I have become intimately familiar with both its pros and its cons. We designed this with a capsule collider for the body so the head could nudge around corners if you just nicked them, and a box collider on the feet so we didn't slip off ledges if we stood right on the edge. But this means that if you jump into a corner at just the right angle, you're going to get stuck because the floor ends up in that little crevice that we created between our colliders. We've also been relying on a dynamic Rigidbody 2D on our player. We calculated gravity ourselves to ensure that we got a good feeling jump, but using a dynamic Rigidbody means we were relying on the physics engine to deal with collisions. And the issue with this is we're giving away control to the physics engine, and we're having to fight it to get our controller to do what we want sometimes. What happens when you try to walk on slopes? Why do you sometimes get stuck on the tiniest cracks on the floor? And we could try to code some clever solution to these problems, but again, we'd just be fighting with the physics engine. So today we are going to build a stronger, proactive foundation for our controller without giving any of our control away. This is going to make it really easy to do things like add movement for slopes and let us smoothly follow curved surfaces. Your player will no longer get stuck on the tiniest cracks. In fact, by the end of this series, we'll create the functionality that lets us walk on bumpy terrain and even vault over tall obstacles in our path. But in this video, we are going to refactor what we've already made, and then at the end, we'll add a head bump slide mechanic so that if your player jumps, wall jumps, or dashes into a ledge and they just nicked the edge, then we'll push them over so they clear it. As a thank you to my patrons, this project is available in a state machine over on GitHub, which is nice because state machines make controllers a little bit easier to debug, to manage, and to extend and add abilities onto later. If you want to play around and see if you like how this controller feels before committing to following this series, it's over on itch.io, link is down below, so grab a controller and test it out if you like. And with that, let's get into it. Ready? Let's go. So we're going to start off right at the fun stuff. We're going to pick up right where we left off in part 2. We're going to go ahead and change our Rigidbody to kinematic, and we no longer need a physics material. We do not need separate colliders. We're just going to add one to our object here. This collider is not actually going to be used for collisions, but it will be used to figure out where we are going to cast our rays. So make sure you position it tightly around your player however you like. Now let's open up our player movement stats script. We're going to rename these here to something more appropriate. If you're using Visual Studio, then Control-R will let you rename things and change all the references at the same time. We're also going to add this here for our new visualizations that we're going to create. And we no longer need any of these. So that's already going to give us a whole bunch of compiler errors. That's fine. We're going to have a lot more before we actually start fixing them. But right now we're going to create a new script called Movement Controller. This is going to be the backbone of our new architecture because this one is going to deal with collisions and move our player based on the velocity that we pass in from our player movement script without letting them pass through walls or the floor. So collision padding is extremely important for this kind of controller. You can think of it like a buffer zone around our collider so that when we collide with other colliders, it's not going to be too tight, which could result in jittery movement of the player, or it could end up making them feel sticky or something like that. This is going to keep everything feeling smooth. And all the rest are pretty self-explanatory, so let's just dump them all in here. We are going to create a little struct called RAYCAST corners to make it easier to reference where we need to shoot our raycasts from. And then in awake, we'll grab the references that we need. So the first two methods that we'll need are update raycast corners and calculate ray spacing. We're going to shrink our bounds inward slightly using our collision padding, and then we're going to update all of our raycast corners. And we need to do this every time we move because bounds are in world space, not local space. So when we move, the positions are always going to be different. So we have to update them. As for the ray spacing, this is going to take our number of horizontal and vertical rays and space them apart evenly along our box collider. So we only need to call calculate ray spacing in start, and we'll call update raycast corners every single time we move. And we're also going to reset our collision states right after that. We're just going to turn all of our isColliding bools to false. And it's at the end of this method where we'll actually move our player. We're using move position because it gives us complete control over our movement, but it also respects the physics system, which means as fixed update runs and gets the position of every collider in our game, our player's new rigid body position will be marked correctly as well. And that's important because we're going to fire RAYCASTs, which are also a part of the physics system because they interact with colliders. So doing it this way, everything that we need to do is going to be properly synced. And you need that because if anything is out of sync, we can get clipping or weird jittery movement. Now, before we move, we actually need to check to see if we're colliding with anything and resolve our velocity if we are. We need to check in front of us, above us, and below us. So for the resolve horizontal movement, and by the way, notice that we're passing in the ref keyword, meaning we're not just creating a copy of the velocity variable and changing that. This will literally change our velocity variable, the one that we pass in. So first we get the direction and length of our ray. Notice that our length is actually dependent on our velocity, which is important to ensure that our rays can always properly detect colliders in front of us. So now we'll loop through all of our rays. We'll grab its origin and increment it upwards because again, these are our horizontal rays, so they're traveling up the side of the player's body. Then we actually cast our ray. If it hits something, well then we actually adjust our velocity on the X so that it stops collision padding distance away from the wall. Then, since we're against a wall, we can adjust the length that any of our future rays in the loop can be since we're flush with a wall already. And then we update our collision pools based on that. And this is optional, but if you want to be able to see your wall hit rays, we'll add this here. The length of these rays are controllable with our extra ray debug distance variable, just so that they're a little bit easier to see. And if any of those individual rays hit anything, they will be cyan, and if they don't hit anything, they'll be red. Okay, let's resolve our vertical movement. This is going to be very, very similar. We get our direction and our ray length. Then we're going to loop through all of our vertical rays, determine the origin based on our direction, and then notice that our ray origin is being incremented not just by our ray spacing, but we're also adding our velocity on the X. So the rays, they're not being cast straight down from the current position of the collider, they're cast from where the collider will be after it moves horizontally, which is incredibly important for stability, especially on things like slopes. All right, now we cast our ray. And if it hits anything, same thing, shorten our Y velocity so that we're just collision padding distance away, and then pass in the distance the hit was from the ray to be the new ray length. And we'll set our collision pools. And again, this is optional, but it is really helpful to be able to debug stuff when you can visually see what's going on. And we'll separate our isGrounded rays from our head rays. For the ground, we'll do same as before. Controllable length for the visualization purposes. And if the rays hit, they're going to be cyan and they'll be red if they don't hit. And for the head rays, we're adding a check for the first and last rays above us, and we're making them magenta if they don't hit and green if they do. It's nice to make these corner ones stand out for the head bump slide that we're going to do later on. And finally, we'll just add a couple of helper methods to the class for our other scripts. All right, and that is it for this script. Now let's open up our player movement. We can get rid of our feet reference and rename the body collider to just call. We'll make isFacingRight a public property because we may need this in other scripts. We're not going to be using any of these variables here anymore. We're not going to use horizontal or vertical velocity anymore. We'll instead use a public vector2 called velocity. We're also going to need access to our movement controller. as well as several input variables, which is going to make it easier for us to decouple our input from our fixed update calls. You always want your input in update to ensure maximum responsiveness. And in awake, we can get a reference to our movement controller. And now we're going to move all of these into fixed update, everything but the count timers method. But we're going to add a parameter to this. And while we're here, we'll go ahead and update our input variables. In fixed update, we can remove the collision checks method. And actually, let's just go ahead and remove all of those methods because we will not be using those anymore. The move method can be renamed to HandleHorizontalMovement, and we'll call it up here and pass in a time parameter there as well as to all of our physics calls like this. Fall can go down here. We actually do not need that is grounded as false check there. Right now, this handle horizontal movement function is a mess. We are going to rewrite it to be better and actually fix a bug at the same time. So just remove all of this. We'll rename apply velocity to clamp velocity. We'll replace the old velocity variables with the new ones. And remove that last line. We move with our other script now. And speaking of which, after that method, we call our controller.move and make sure to multiply our velocity by time.fixed delta time. And now that our physics methods have all run, we've used our input so we can reset it. Now I mentioned we were going to rewrite our move method or our handle horizontal movement method. All of that awkward logic that we had before should have been baked into this method. So if we're not dashing, we check to see if we need to turn. And if our move input is over our threshold, then we find our move direction and multiply that by our max speed so that we don't get any awkward partial speeds if you are using a gamepad and you're just slightly moving the analog stick. This is going to make it a pure stop or go based on whether or not you're past the movement threshold. Then we calculate our acceleration and deceleration based on whether we're in the air or on the ground, or if we're currently wall jumping. Then finally, we lerp our velocity based on our acceleration to make them reach our target velocity. I also forgot to change the old parameters in here. We only now need time step. Okay, so at this point, we should have a lot of errors. And now we get to do the thing that makes my possibly diagnosable OCD happy and fix all of those red dots. We're going to go through method by method. You can go ahead and do a find and replace, whatever you want. Use Copilot's autocomplete. It's pretty helpful for this stuff. I'm just going to go through it method by method for you guys, just in case you need to see something specific or you miss something. But essentially, any old is grounded or bumped head or is touching walls bools, they get replaced with our new helper methods from our movement controller. Our old velocity variables need to get replaced with our new one. And any of our old input needs to use our new input variables that we just set up. Plus, there's going to be just a couple of little tweaks along the way. So in land check, we'll update our velocity. We can also get rid of this ground check, as well as this line here. Our new system takes care of that. And replace this is grounded up here. In fall, we'll add our parameter in there and replace our time with it, and replace our velocity reference. In jump checks, replace all of our input calls, our collision variables, and our velocity variables. In initiate jump, we replace our velocity. In jump, we add our time step parameter and replace our time.fixed delta time references with it. And replace our collision variables and our velocity references. In wall slide check, again, collision and velocity references. In wall slide, add a time step parameter and replace that, and change velocity. In wall jump check, replace collision, velocity, and input. In initiate wall jump, we can replace our velocity calls. We can also get rid of this here and replace it with our much simpler helper method from our controller. In wall jump, add a time step and replace time.fixed delta time, as well as replace collision and velocity variables. In should apply post wall jump buffer, we can get rid of the is not grounded check and replace our collision calls. We're nearly there, by the way. In our dash check, replace collision and input. In initiate dash, replace your input. And in dash, yet again, add the time step parameter. We're going to replace time.fixed delta time with that and replace our collision and velocity variables. In count timers, we also need our time step parameter in there and replace all of our time references. And in draw jump arc, replace our feet collider reference with our single collider reference. Okay, we should be good now, except I made a little typo here. And actually, if you were following along, I misplaced my brackets over here as well, which made wall sliding fail on the left side. So we'll fix that. All right, so in the inspector, we're going to plug in our collider reference and add the movement controller to our player. And now go ahead and test it out. It should behave exactly the same as what you had at the end of the last video, except you now have a RAYCAST based controller instead of a dynamic Rigidbody controller. And if your player was ever getting stuck on little cracks in the ground, even like perfectly flat ground on tile maps and things like that, those problems should be completely solved for you now thanks to this new architecture. Now, before we go ahead and add anything new, there's actually a few other little things I'd like to tweak that were really bugging me. Go down to your dash function, and right after this block here, we're going to add this, basically making our velocity 0, but just not quite if we're dashing horizontally. Having a velocity of 0 actually makes our is grounded return false. So if you had a land animation or anything like that that could be triggered from this when it's finished, it's pretty annoying. So that's why we're not setting it to 0. But now that we've done that, this fixed our problem where before, when we dashed off of a ledge, we would immediately just start falling, which to me feels wrong for a dash. So now when we actually dash off of a ledge, we will go perfectly horizontal until the dash is complete. Okay, one more tweak. We're going to go to initiate dash. We're going to add this so that when we're grounded and we're dashing downwards and horizontally, then we'll just change it to horizontal. That way, if you're on the ground and we dash down diagonally, we're not going to dash into the ground. This is going to correct itself and just go horizontally, which in my testing felt a lot better. Also up here, right after we set our dash direction, call the turn check method. Because before it was possible, although slightly rare, that you could end up dashing backwards, and that's not going to happen anymore. And for the final fix, we already have jump buffering and wall jump buffering implemented, but we don't actually have any dash buffering. I feel like if we've used all of our air dashes and we hit the dash button just a hair before hitting the ground, then we actually should dash once we hit the ground to keep our controller feeling fair and keep our controller feeling responsive. So first, back in our move stats, we'll add a dash buffer time. And now back in our player movement, we need a dash buffer timer. Now we need to decrement that timer in our count timers function. And now in the dash check function, we can simply set our dash buffer timer if we press the dash button. And then if our dash buffer timer is greater than 0, then everything else is going to run. And to finish that off, we need to reset the buffer timer. So set it to 0 after each initiate dash call. Okay, so I promised you guys a new ability. So now we are going to implement a proper head bump slide mechanic. So in move stats, we're going to need all of these. As well as a new debug pool. Now, in our movement controller, we're going to need a few more collision variables. And we can reset those here. And we'll call our new method right after we reset our collision states. So there's nothing too special going on here. We're going to cancel out of the method if we're moving down or if we are not using the option. And then we'll set up the distance, the size, and the origin for a box cast. We're using a box cast mainly because it's the easiest to see and debug. If this tiny little box on the top of our heads actually hits the ceiling, then our automatic rule is going to be no sliding, that's just a head bonk, and we'll just go straight back down. And again, optional, but if you want the visualization code for the debug lines, here you go. Now we're also going to need some changes to our resolve vertical movement as well. So we'll add these two bools near the top. And then if we are colliding above, we want to check our first and last rays on our head, meaning the left corner and the right corner of our head. We use those to calculate which direction we need to slide in. However, before we do that, we have to cast a ray to check if there's actually an open space for us to slide into. If there's no hit, meaning there is space for us, then we will set our head bump slide direction. And finally, after the for loop, we need to set our is hitting both corners pool. Okay, so we have the collision portion of that all set up. Now we just need to actually implement it in our player movement. So here are the new variables we'll need for it. And we're just going to go ahead and add all the checks and guards and everything in right now so that we can test it immediately after we create the actual method. So at the top of handle horizontal movement, we're going to cancel right out if we are head bump sliding. We also add that bool as an OR option in our land check. And we also want to set it to false right here. In jump, we're actually going to delete this and replace it with something more robust. So we set our is head bump sliding to true here based on all of our checks. And if we're not sliding, then we kill our vertical velocity, but same if we are sliding because sliding is only horizontal movement. And finally, we can wrap everything right up until the jump cut in this if just finished slide is false. This is to ensure that we don't need to worry about single frame time differences. Now we need to do almost the exact same thing in wall jump as well. It's basically the same thing, we just need to set the wall jump variables instead of jump variables, but the whole idea is the same. And again, we wrap the rest of the method up until the wall jump cut in this if statement here. Dash is mildly different. We can do all of this right before the timer is even incremented. Same checks as before, but there's just a few more variables and flags that need to get set here. And we don't need to wrap anything in that single frame check on this one. So our jump start Y will get set right at the start of initiate jump. as well as initiate wall jump. And finally, we will create our actual handle head bump slide method. So we'll cancel out if we are not head bump sliding. Now, if we want to stop head bump sliding, either we don't have a direction, we did not bump our head, we're hitting the ceiling center, or we're hitting both corners. If any of those things are true, then we are no longer head bump sliding, and we can stop the X velocity so that momentum does not continue to carry us. And if we actually hit the ceiling dead center, then we stop the Y velocity as well. Otherwise, we calculate how high we need to continue to finish the jump that we started and apply that to our velocity. And return after all that. And if we make it past, well then we're head bump sliding and we move our velocity on the X until we make it around that ceiling. And finally, don't forget to actually call the method in fixed update right after handle horizontal movement. And I also missed this one bool reset here, which we need right at the top. Now, there are a few issues that we're going to have to address since we changed the architecture to make sure that everything is feeling solid and working 100%. My goal from the beginning with this controller was for it to be 100% deterministic, which means assuming the exact same starting inputs and conditions, the controller will always produce exactly the same outputs and results frame for frame. My jump height, for example, produces the exact same height output every time, no matter what. And I've learned a lot about this topic since I started this video. I wanted to post this over a week ago, but I realized it was not in the perfect state that I wanted it to be in. So we're going to make a few adjustments and hopefully learn a thing or two along the way. We're going to start with our handle head bump slide. We are recording our transform.position.y here, but we're moving our rigidbody.position in fixed update. Transforms and rigid bodies update at different time intervals, which means there are certain frames where there will be a difference between the two. It'll be small, but it's small enough to ruin the perfection that we are going for. So we should be grabbing our b.position.y instead. And same thing in our initiate jump function. We want to record our jump start y as our rigid bodies position.y, not our transform. And we need to change that in our initiate wall jump as well. And again, with determinism in mind, we're going to move our timers from update to fixed update and update our time step in there. In certain places in our timers function, we're actually checking for grounded states, and we cannot guarantee that those are going to be 100% accurate unless we're checking those during a physics time step, because those states only update during a physics time step. In our fall method, I made a big mistake. I thought we could take our is grounded check out of here. That was very, very wrong. We definitely need to be ensuring that we are not grounded to know when we're falling for hopefully obvious reasons. All right, next we're going down to the head bump slide. And when we jump into a head bump slide, we calculated the distance that we needed to travel to reach our jump apex, but we forgot to add our compensation factor in there. So we can calculate that like this. And then plug that in here. And there's also an update we need to make this work better for dashes as well. So first off, we're going to add this bool up here to know when we're head bump sliding from a dash. And we also want to create a dash start Y float so that we can track where we were when we started the dash. We can set the bool to true here when we are dashing and we trigger a head bump slide. We can also set our bool to false in our jump here and here in our wall jump as well. And our dash start Y, we can just grab our rigid body's Y position at the start of a dash like this. But we're also going to pre-calculate the full distance that our dash is able to travel so that we can just grab it whenever we need it. So we did that with our initial jump velocity. So to replicate that, we're going to go back to our player movement stats script. We'll just make it a property here. And then in our calculate values, let me type this all out and then I'll explain because it might seem a little bit confusing. So you'll notice we're grabbing a dash time and a dash cancel time. The reason for that is because that's how our dash is built. If we're dashing vertically, we first have the dash, and then when that dash finishes, just like with our jump, we lerp our velocity from what it is to 0 over a certain amount of time. We need to account for both of those things in order to get our full dash apex. And the reason we're rounding these numbers by time.fix.delta time is to ensure that we are getting real world numbers. If you, for example, set your dash time to 0.11, well, fixed update only runs every 0.02 seconds, which means that you won't dash for 0.11 seconds, you're going to dash for 0.12 seconds since we moved our timers into the fixed update. So this is just going to round it to the nearest 0.02 so that we're calculating the actual real world amount. Hopefully that makes at least some sense. Now back to our head bump sliding. Now we'll do all of this here if we are not sliding from a dash. And if we are, then it's going to be very similar to the jump. We calculate our target apex from a dash and calculate our remaining height needed to finish the dash from our head bump slide. If we don't have to go up anymore, then just change it to 0 so that we immediately start falling. And if we still have to travel up, then calculate the required velocity to get there and change our velocity. And we're going to set our slide from dash to false here at the end as well. And we'll just move our just finished slide to down here as well. Now that we've done all of that, we should properly be able to head bump slide whether we jump or dash into a ledge. All right, next, we also need to add a resting gravity amount, something that's applied even when we're on the ground. So we're going to tweak our land check method slightly to do that. We'll wrap up the whole thing in this is grounded check. And if our velocity is less than or 0 while we're on the ground, reset it to our standard gravity rate. All the research I did indicated that it should be a small negative number like -2. All right, this next one is just some housekeeping inside reset dash values. We're going to reset our fast fall release speed, our fast fall time, and our dash direction here. And in our land check, just call it and get rid of this block here. This is not going to change any behavior. I just found that it made debugging things a lot easier, and this cleans up the numbers in the proper place at the proper time. And we want to add a quick guard here at the start of dash. If we just finished sliding, which only lasts a single fix update step, then we cancel out to avoid getting any extra velocity that we don't want. Now, with the wall jump, since we updated our architecture, you might notice that if we're wall sliding and we turn away from the wall for a moment and then press the jump button, we still get our jump via our wall jump post buffer. However, we're not getting the X velocity in the direction that we should. And this is because of our simplified logic here in our initiate wall jump. This logic is totally fine for a regular wall jump, but for our wall jump post buffer, we'll always be facing away from the wall. And so it's actually pushing us in the wrong direction back into the wall, which we do not want. So we're going to set up an integer called last wall direction. And we'll set that whenever we are facing a wall or our wall sliding. Then in our initiate wall jump, instead of just getting our wall direction here, we'll multiply our jump direction by negative our last wall direction. All right, and with that correction, now when we used a post wall jump buffer, we should actually be moving away from the wall, which is a lot less jarring. It's much nicer. One more tiny correction. We don't actually need to wrap this in a check here. It's actually more accurate and we'll get better results if we just always decrement the buffer timer. All right, next thing I want to change, it's not fixing a bug, but it is fixing poorly written logic, and that's just kind of confusing. And we're going to simplify it and make it easier to understand. We have a variable in our movement stats called number of allowed jumps, and we're kind of very awkwardly combining our regular ground jumps and air jumps into this one variable. So we're going to rename it to number of air jumps allowed, and we should let 0 be an option now, and we'll set the default to just 1. And back in our player movement, change number of jumps used to number of air jumps used. In our jump checks, we've got a couple of changes to make. The integer that we're plugging in here for all 3 initiate jumps need updating. So now it's going to be 0, 1, and 1, because we only pass in 1 when we actually are using an air jump. We can get rid of the -1 here. In our initiate jump, we can rename this to number of air jumps used. In our stop wall slide, you can get rid of this. And in our dash check, all of this really confusing logic can go because we just massively simplified things. And while I was recording, I accidentally did the same check twice here. So if you didn't catch that already yourself, just go ahead and change this one to is hitting both corners. And the very last thing that we're going to do is actually improve our handle head bump slide method just a little bit. I tested this, and yet during the recording of this episode, I still got some inconsistencies that I didn't like. So I paused and I wanted to figure out how to make it better and then re-recorded this section. Sometimes it would just straight up fail because the jump method and this method were actually fighting each other and constantly setting is head bump sliding to true and false and over and over and over, just back and forth. So to solve that and make sure that that never happens, we're going to modify our approach just a little bit. So first we're going to get rid of this and this if statement and these lines and this here as well. So we'll check if we should be sliding. Set our bool and set the head bump slide direction. And if we are head bump sliding, then we're going to stop our velocity.y because it's supposed to only be sliding us horizontally. And now we check if we should exit a head bump slide, and if we should, set it to false and stop our horizontal velocity so that we don't have any carried momentum from that. Now this logic is still good, so we can move it in here. Get rid of this return. And then this will be in an else. And move these two lines up here. And we can actually simplify this a bit by getting rid of the if our remaining height is less than or equal to 0 and just check if it's above 0. So now, again, only this method controls when head bump sliding starts, so it shouldn't be able to fight with other methods like jump and wall jump anymore. Now over in jump, you can clear out these lines, and we'll do the same thing with the wall jump. And in dash, same thing, we get rid of the bool and make sure that we are setting slide from dash to true here. Get rid of the slide direction and these two last lines. And there we go. Congratulations on making it through. I know that this one was absolutely massive because we had to reconstruct an entire architecture from the ground up. It's a massive, massive thing. But what you should find is that this player controller will be much more stable now. We have full control over everything. We have this nice slide as well. I'm hoping that in the coming weeks, I'm going to be able to do a few more of these and we'll handle slopes, smooth ground, and the ability to walk over bumpy ground as well. So stay tuned for all of that. And again, if you want access to this project in a state machine, it's available right now to my patrons. Thank you guys so much for watching. I'll see you in the next one.